Right, we're looking at Power Systems grade 12. The topic is transformers. And the first question is, name two types of losses that occur in transformers. And we get hysteresis and eddy current losses. These are the two types of losses that occur in transformers. Hysteresis, the phenomenon in which the value of a physical property lags behind the changes in the effect causing it, as for instance when magnetic induction lags behind the magnetizing force. So this is the after effects of magnetism caused by mutual induction. Eddy current loss, also known as Joule losses, is a phenomenon that occurs when a conductor is exposed to a varying magnetic field, resulting in the generation of circulating currents within the conductor. But let's rather keep it to eddy current losses. Draw a fully labeled diagram to show how three identical single-phase transformers may be connected to operate as a three-phase delta star unit. So we're going to draw three single-phase units to represent a delta connection on the primary and a star connection on the secondary. We have a three-phase delta star transformer, but we're going to draw three single-phase units to represent a delta star connection. There's our single-phase transformer. Now we have three of them, three on each side. In delta, it's a series connection. We go from one point to another. On our primary on the left, we're going to go from one point to another, and from the 2 points to the third point. Please note I made a mistake. And from the second point all the way to the third point. On the left side, L1, L2, L3. On the right hand side, we also have L1, L2, L3, but it is a star connection. All the one sides of the star connection must all go to a common, all connected to a common point. Join the common points up, and that will form the neutral. The star is a 4-wire system. L1, L2, L3, and the neutral. Question 1.3 reads, the delta connected winding of a three-phase transformer is supplied with 11 kilovolts. The secondary winding is star connected and supplies 400 volts to a balanced star connected load of 10 kilowatts with a power factor of 0.8. Calculate the following at full load. 131 says the total kilovolt amps of the load. So because we see kVA, that's an indication that this would be apparent power. First step is to draw a little diagram putting all the values in the correct places, that is on the primary or the secondary side. This is the first step in order to understand the question. The question said a delta connected primary and star connected secondary. The primary is connected with 11,000 volts, 11 kilovolts. In delta connections, the line voltage is equal to the phase voltage. The power supplied to the load is 10,000 watts, 10 kilowatts. Notice that this is true power because of the unit watts or kilowatts. The power factor is equal to 0.8. The line voltage is 400 volts. On the secondary side, notice we'll have to find the phase volt. 131, the kilovolt amp is what they want us to calculate, the total kVA of the load, and this will be the apparent power. The apparent power is S. Power is equal to VI cos theta. True power is P. Apparent power is S, which is equal to VI. We have to make S subject to the formula. So S is equal to P over cos theta. Cos theta is the power factor. 10 kilowatts was the true power. The power factor given 0.8 is the power factor. Divide that in our calculator, we 12.5 kVA. 132 wants us to calculate the secondary line current. We need to make IL subject to the formula. That's going to be power divided by root 3 VL cos theta. Substitute our values. Power is 10,000. Our secondary line voltage is 400. And our cos theta is 0,8. So notice we are working on the secondary side because we wanted to find the secondary line voltage. Sorry, the secondary line current is what we are trying to find. So that means we would use the secondary line voltage. In our calculator, 18,04, don't forget the unit amps. The unit is very important to get the mark. 133, the secondary phase current. It looks very tricky but so simple. With star connections, are the currents the same or the voltages the same? The voltages are different and the currents are the same. Therefore, I phase 2 is equal to I line 2 and our value is 18,04. Another question that they could have asked here is calculate the phase voltage. Then all we do, we'll take the line voltage and divide it by root. Okay, and that is one of the other questions that I could have asked. Question 2.1, the two purposes or the dual purpose of the oil. Transformer oil's primary function are to insulate and cool a transformer. It must therefore have high dielectric strength, thermal conductivity, and chemical stability, and must keep these properties when held at high temperatures for extended periods of time. So the oil is very similar to the oil used in a car engine. What's the purpose of the oil? For insulation purposes and for cooling purposes. That is the dual purpose of the oil. 2.2's question. A new school is under construction and will be fed from 11 kilovolt supply. The school requires a single phase and a three-phase supply. Draw a schematic diagram to show how the primary and the secondary windings of the transformer supply the school will be connected. 2.3. Three single-phase transformers are connected in delta star to form one three-phase transformer, as we did above. The supply voltage is 11 kilovolts and the turns ratio is 45:1. Ignore the transformer losses and calculate at full load the secondary phase voltage. So notice the transformer ratio is always primary is to secondary. So 45 will be N1 and 1 will be N2. We always start with the diagram. We have a line voltage of 11,000 volts on the primary left hand side, incoming side, and we have a transformer ratio of 45 on the primary is to 1 on the secondary. So our voltage is directly proportional to the number of windings. So the formula is V1 equals to N1 on the right hand side over V2 on the left hand side equals to N2 on the right hand side. Please note that this formula works only with phase voltages. You cannot use line voltages in this formula. Manipulate the formula to make V2 subject of the formula. Substitute. Note that N1 is 45 and N2 is 1. Correction. 1 over 45. Calculator, 11,000 divided by 45 will get 244,44 volts. This is on the secondary side, V2. This will be a phase voltage. Why? Because the formula only works with phase voltages. So if you put phase voltages in, you will get phase voltages out. Maybe you're thinking and saying, but we used a line voltage in the formula. Notice we have a delta system on the left hand side, on the primary. Remember with delta, the voltages are the... So the line voltage and the phase voltage is 11,000. So we used a phase voltage in the formula. Question 232 wants us to find the secondary phase voltage. 231 was the secondary phase voltage. 232 is the secondary line voltage. We have to make VL subject to the full. Substitute into the final answer 423,38 volts. The next question reads, A three-phase 250 kilovolt amp transformer has a star-connected secondary with a phase voltage of 220 volts. Calculate the power of the transformer with a power factor of 0.8 lagging. So notice here, the power given is apparent power because it is kVA. True power equals VI cos theta. VI is equal to S. We have to make P subject of the formula. Substituting our apparent power times cos theta, which is our power factor. So we get 200,000 volt amps. Don't forget to convert that to kilovolts amps. Divide by 1000. Final answer, 200 kVA. The next question says a 320 kVA three-phase transformer is connected in star delta connection. The delta connected secondary phase voltage is 380 V and the transformer ratio is 10:1. So this one is similar to the one we done above. Pause the video, try it out, and then check the solution. First step is to draw the question. We have a star delta. We have a transformer ratio of 10:1, so the star is 10 and the delta is 1. The first question is calculate the secondary line voltage. With delta we have the same voltage. In the question we are given that the secondary phase voltage is 380, so we have the same voltages. The secondary line voltage is equal to the secondary phase voltage is equal to 380 volts. Don't forget to put the reason delta. Second question is the supply phase voltage. What does the word supply mean? Correct, primary. Okay, so we're using the formula only with the phase voltages. So V1 over V2 equals N1 over N2. Only phase voltages can be used in this formula. Alright, we are given N1, N2, and V2. We are going to calculate V1, make V1 subject of the formula. V2 is 380 and N1 is to N2. That is our transformer rate. 10 turns is 1 turn. Multiply that, 3,800. Because we have a star on the left hand side and this formula only works with phase voltages, this will be a phase voltage. So we could calculate the line voltage. Next question is the supply line voltage, which would be the prime. Right, so V line is equal to √3 times the V phase 1 voltage, the one calculated above. Plug it into your calculator. And so plugged into our calculator we get 6.58 kilovolts. The next question, the load line current. Here we were given apparent power. There is no cos theta in the question. You could use true power formula as well, but then for cos theta you'll place a 1 there, which practically will be the apparent power. Notice that load means secondary, and so we are calculating the secondary line current. We will have to use the secondary line voltage in this question. Right, our power was 320,000 divided by √3. Because we have a delta on the secondary, the voltages are the same, so V phase 2 is 380, but V line 2 is also 380 because the voltages are the same for delta. And that's our secondary line currents, 486.19 volts. The next question reads, calculate the phase current, secondary phase current. Notice we already have the line current. We can definitely find the phase current. Notice that for delta, there are two different currents. So using the formula, I phase 2 is equal to IL2 over √3. Substitute. Our final answer will be 280.7 volts. Describe how the EMF is induced in the secondary windings of transformer. AC voltage is applied to the primary windings. Alternating currents will flow in the windings. This current will produce alternating magnetic fluxes. The magnetic fluxes will link with the secondary winding through the magnetic core. After linking, an EMF is induced into the secondary winding. Mutual induction is the ability of an inductor in one circuit, that's the primary side, to induce a voltage into another circuit, that is into the secondary side. When a transformer primary has alternating current flowing in the conductor, the magnetic field surrounds the conductor and is proportional to the amounts of currents. This force in the first primary side will magnetically connect to the secondary side through its magnetic core, as you can see the magnetic core on the right hand side. After this, there will be a linking of EMF that is induced into the secondary coil. 2.7. Explain why cooling methods and protective devices are effective and efficient for use in transformers. The device does not overheat, life expectancy is not reduced, it isolates the supply should a fault occur, and does not cause damage as a result of a short circuit. So the first two that I mentioned are for cooling. So cooling, device does not overheat, the life expectancy is not reduced, that is for cooling. And for protective, isolates the supply should a fault arise, not causing damage as a result of a short circuit. The next question has to deal with transformer efficiency. So efficiency is equal to the output over the input times 100%. To get the output, all we do, we take the input power and we subtract whatever losses there are, and that's how we get the output. So output will always be a smaller number than the input. So by subtracting the losses, this is how we get a smaller number. Times 100 will give us efficiency in percent. 2.8, the question reads, a 10 kilovolt amp star delta transformer has primary and secondary line voltages of 6 kilovolts and 500 volts respectively. So the word respectively means the one that comes first, use it first. And so the first primary line voltage would be 6,000 kilovolts, 6,000 volts. So first step is to draw our transformer and put in all the values. They also tell us that the power factor is 0.96. Our parent power, which is S, is 10,000 volt amps, 10 kilovolt amps. The first question is the secondary line current. So in this question, if you are going to use the true power, that means we'll need to calculate the true power to use this formula. So by calculating the true power first, and we'll get 9,700 watts as the true power. So we can substitute and continue. We need to make current, the line current, subject of the formula. But notice you could also use a parent power, that will be fine, and then all you'll do, you will leave out cos theta, you won't use it. So you could use the formula below, would also give you the same answer. Substituting our power as 9,700 because it's true power, and our VL will be the secondary line currents because we are trying to find IL. Our secondary line current is 500 and our cos theta is 0.97. Plugging it into our calculator, we get 11.55. The next question is the transformer ratio. Remember that transformer ratios only work with phase voltages, so we'll need to find V phase 1. Remember on the primary side we have a star. Star has 2 voltages. Our line voltage on the primary side is 6,000 volts. Substitute into the formula, calculator, answer. 3,460 volts. Notice this is a phase voltage. We can now use the formula to calculate the transformer ratio. By using V1 over V2, we can find the transformer ratio. Notice with delta we have the same voltages. 6.92, don't forget to make that is to 1. You will note we calculated the true power up above. So the same, use your formula, power equals to S cos theta. The S was 10,000 times the power factor. Next we're going to calculate the transformer efficiency. That's on the right we're going to use. It is very important here to use the true power. So power in will be 9,700. Our losses in the question is given as 81. Plug into the calculator, final answer 99.17%. And that's how we get the efficiency. Right, I hope this video was easy enough to understand. Enjoy.